Once we've calculated our correlation coefficient for our sample, we're going to want to determine whether there's enough evidence to decide that we can use this for our population correlation coefficient rho. We're going to look whether it's significant or not statistically. So in other words, based on a few pairs of data, can we make an inference about this population for all of the data pairs? So remember that you're using sample data to make a decision about our population data. So it's always possible that your inference may be wrong, even if it's statistically significant. Even if the evidence points towards it being able to be used for the population, it doesn't mean that it's always going to be correct. So in correlation studies, the small percentage of time when you decide that the correlation is significant, when really it's not, is called your level of significance. This is typically set at alpha equals 0.01 or alpha equals 0.05. In fact, this is something you'll see a lot of when we're doing Chapter 7 on hypothesis testing. Based on this, you'll probably decide that your population correlation coefficient is significant when in reality, 5% of the time it's not going to be. That means 95% of the time it should. And that's really where that unknown comes from in statistics, is that even when we say, okay, the evidence seems to point to this, there's always that 5% chance where it may not, even if you did everything correctly. When alpha is 0.01, this would be the same idea, except for there's 1% chance that you are incorrect, even if you did everything correctly. So looking at this slide here, you can see that we have this table. This is called the Pearson correlation coefficient table. So for a correlation coefficient to be significant, its absolute value must be close to 1. So in this case, we're going to be taking the absolute value. So to determine whether the population correlation coefficient rho is significant, we're going to use the critical values from this table. A portion of the table is, you can see here on this slide. So you take the absolute values, that's what the bars around R is. If this is greater than this critical value that you see on the table, then this means that you are statistically significant, that you can, in fact, infer that you can use this for an estimate for your population. If you determine that the linear correlation is significant, then you'll be able to proceed to write an equation for our linear models, which we'll be looking at in the next section. How do we actually do this? Well, first, step one, you're going to want to determine the number of pairs of data in your sample. So how many data pairs do you have in your sample? Second step is you need to specify what your level of significance alpha is going to be. So generally the go-to is 0.05, but you may decide you want to use 0.01. Then we're going to look up on our table and find our critical value, and then we'll decide whether the correlation is significant or not based on that. And then from that, we can interpret our decision in the context of the original problem. So let's go back to that table really quick and talk about that for a second. At the top, you're going to see n, alpha equals 0.05, and alpha equals 0.01. Along the left-hand side, you're going to see numbers 4, 5, 6, through about 29 in this table, though other tables will continue on. This is just a snippet of a table. So this means that if you look at the value that's circled here, we have n equals 25. That means we have 25 data pairs, meaning we have x1, y1 through x25, y25. The alpha is 0.05 is highlighted. This gives us a number of 0.396. Meaning that as long as our correlation coefficient is larger than 0.396, we have enough evidence to say this is statistically significant at the alpha equals 0.05 level, or the 0.05 level of significance. So now let's do a quick example. In previous example, that was the GDP example if you go to the other video, we used 10 pairs to calculate correlation coefficient of 0.874. So if we have alpha 0.05, is this statistically significant? So we have n equals 10. We have an R value of about 0.874, and we have an alpha of 0.05. Now remember, when we're doing this, we always want to use the absolute value of R. Well, R is already positive, so this really doesn't change it for this example. But if we have, for example, was a negative correlation of negative 0.874, in this case, we would take the absolute value because we only want to know the magnitude. We don't really care about the direction when we're looking for significance. So the fact is we have n equals 10. So now let's go back to that table, that snippet that we had. And if we go down to n equals 10, we go over to alpha is 0.05, we get a value of 0.632. So this is the value that we're going to compare this to. So we're going to take our 0.874, which was equal to the absolute value of R, and we're going to look at, is our value larger than this value or is it less than? In this case, our value is larger than this, meaning that it is statistically significant. Now I want to revisit when we talked about correlation and causation. So the fact that two variables are strongly correlated does not in itself imply a cause and effect relationship between those variables. And of course, a more in-depth study would usually need to be done to determine whether there is a causal relationship between these variables, specifically with certain conditions to see is X causing Y or is it just that they are related. So when there's significant correlation between two variables, a researcher should consider a couple possibilities. The first possibility is there is a direct cause and effect relationship between the variables. If you find a high correlation that seems to be statistically significant, then in fact it may be a causal relationship. Now, we don't have enough evidence to say that right now, but it is one of the possibilities. For instance, consider a relationship between gross domestic product that we looked at and our CO2 emissions. Then it's reasonable to conclude, based on this, that as countries have a higher GDP, they emit more CO2. Now, does it mean that there is a cause and effect relationship? Well, not necessarily. Maybe we've got it backwards. Maybe the relationship is actually caused by the countries that produce the most CO2 end up getting a higher GDP. And this leads us to possibility number two. Is the reverse cause and effect relationship between the variables the answer, right? So instead of countries that have higher GDP emitting more CO2, maybe countries that emit more CO2 end up earning a higher GDP. A good example of this would be the Old Faithful data, which you'll see when I do the applied examples of calculating correlation in linear models, is that it is data that has the eruption time of the Old Faithful geyser at Yellowstone National Park and the waiting time between eruptions. And in this case, you might think, okay, well, the amount of time that I wait might increase the amount of time that we have an eruption. But it actually could be the other way. It could be the fact that if I have larger and longer eruptions, maybe it takes more time before the next eruption can occur. The third possibility is it possible that the relationship between the variables can be caused by a third variable or perhaps a combination of other variables? This would be something where you're seeing a relationship between two things, but there's some other underlying variable, possibly what's called a latent variable, which means that it's something we can't maybe directly measure, but it's actually kind of affecting both of these. Or it could be a whole combination of measures that are actually leading to these to have a relationship that change with or against each other. And then possibility four is it possible that the relationship that you're seeing is just a coincidence? For instance, let's say that you find a correlation between the number of animal species in an area and the number of cars that people own. You might think that, okay, well, they seem to be related because as the species goes up, the number of owners goes up. But really, it's probably just coincidence. Or it's even possible that maybe there's some underlying factors that are actually affecting both of these things. And this possibility of coincidence is something you always have to take into account, because remember from probability that we studied earlier, even if you have complete randomness, it's still possible to flip 20 heads in a row when you're flipping a coin. It is unlikely, but you can definitely get times where your data will give you the wrong answer, even if you took all the right steps. So just always be aware that this is one of the possibilities. So in conclusion for this section, first, you want to determine which of the cases above is valid for your data, and this can actually be very difficult to do. For example, let's consider an example. A person breaks out into a rash after eating shrimp at a certain restaurant. So this happens every time the person eats shrimp at this restaurant. So the natural conclusion that you might have is that the person is allergic to shrimp and should stop eating shrimp. However, they go to an allergist and it turns out that they don't have an allergy to shrimp. Why might that be? Well, it could be something else that's actually causing that relationship. It could be, for example, a certain spice that they specifically put onto their shrimp. So maybe having shrimp without that spice, they wouldn't have the reaction. So just because it seems pretty clear cut doesn't always mean that it is. and it does usually involve more study to determine if there's a causal relationship between two variables. And then just as a preview, I just wanted to show you what the Old Faithful data looks like. Now, I did take this data, which is really just two columns, X and Y, and I just had it so it keeps going further and further over every time I got to the end of the page. So you can see all the data. It's 272 data points, so 272 X, Y combination. And if we were to plot this, we would get something like this. You see this scatter plot. Now, it's pretty clear to see that there is a positive correlation. And I will tell you, just a spoiler, it's a fairly strong positive correlation between the waiting time and the eruption time of Old Faithful at Yellowstone National Park. In fact, you can see it right here of an R value of 0.91. So now, if we were to go to our table to determine whether this is statistically significant, you would have to go either to a table that has a lot of values, up to 272 if you're in, or generally what's going to happen is you're going to use the next value you can from it. Meaning that if we were to use the table that we have in this class, I think it goes up to 100 before it jumps to infinity. So basically, you would have to use that as your value to look at whether it's statistically significant. I want you all to try that, and I will tell you though, the answer is yes. But I want you to try to see if you can look that up in a table to figure it out. And that's it for correlation coefficient. We looked at scatter plots, we looked at how to calculate correlation coefficient, specifically by hand, and we looked at, once we have our correlation coefficient, can we determine whether it's statistically significant to estimate our population parameter. Next, we're going to be looking at how do we create a linear model using this same sort of data, and then I will also have a video where I'm going to go through a bunch of different tools that you can use to try to calculate these things. For example, Excel, R, Python, Julia, SPSS, a whole bunch of them that I did just so you all could have a bunch of examples on how to do all of these. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.